Hi everyone, I'm Chujun Lin. I'm a postdoc at the Department of Psychology and Brain Science at Dartmouth College. Today, I will talk about our new work with Mark Thornton on how people infer others' mental states and traits. Here, by mental states, we refer to a person's momentary states of the mind, such as emotions and thoughts. Traits refer to more enduring characteristics of a person, such as whether someone is young, extroverted, or trustworthy. We will show you evidence on how mental state and trait inferences are causally linked. I will first walk you through the motivation of this work, and then present 4 studies. All studies are pre-registered on Open Science Framework. You can access the data and codes via this link. Our preprint will be coming soon. First, why are we interested in mental state and trait inferences? Because they are both independently important for understanding human behaviors. Here, I'm going to show you an example that illustrates why understanding others' mental states is important.
Let's see. It's a boy!
Good boy!
Yes!
Now, you might not even be explicitly thinking about it, but our brain has already filled in the gaps. Why did the little girl suddenly started screaming, crying, and drop to the ground? She was probably feeling very sad and disappointed. But why? Well, she probably does not want a baby brother. Let's see whether that is the case.
Tracy wanted a girl, obviously.
Our guess is not bad. This example shows why inferring mental states is an important tool for us to understand other people's behavior. Here is an example about why understanding others' traits is also important. If we know that a coworker is a serious person who does not laugh that much, we will likely not attempt to tell a joke in the next meeting with this coworker. That is, understanding our coworker's traits saves us an awkward moment of them not laughing at our jokes. These two important human cognitive processes of inferring mental states and traits have also inspired AI research, like in the domains of human-robot interactions and multi-agent systems. For example, in this very interesting paper by Robin Novis and colleagues, they proposed a machine theory of mind network, in which an agent learns to understand other agents. In this network, there are 3 important components. The character net, which learns the general types of the other agents. This is like humans learning about other humans' personality types. The mental state net, which learns agent-specific mental states online. This resembles human inferring the mental states of other people given the situation. Based on the character net and mental state net, this agent predicts the subsequent behavior of other agents. This resembles how humans predict others' behavior by understanding their mental states and traits. So why are we interested in the relation between mental state and trait inferences? Because the connection between them is likely to have important real-world implications. For example, when judges evaluate the legal responsibility of a defendant, it is critical to infer the defendant's mental state at the time of committing the act. On the other hand, people form trait impressions of others based on superficial cues, such as their faces. We are likely to think that someone is trustworthy simply because their face looks more trustworthy. If inferences of mental state are affected by inferences of traits, then legal decisions might be biased by how the defendant's face looks, which recent studies seem to suggest that is the case. This example shows why understanding the connection between mental state and trait inferences is important. Indeed, recent research suggests such a connection. For example, in one neuroimaging study, researchers obtained the brain activity patterns when participants thought about famous people. They also obtained brain activity patterns when another group of participants thought about various mental states. In addition, they asked another group of participants to rate how often they think these different famous people would feel each of the mental states. With this data, they computed the weighted sum of the mental state patterns by the mental state frequency for each famous person. They tried to predict the brain activity patterns when participants were thinking about how these famous people are like in general. With this weighted sum mental state brain activity patterns, they found that matched target patterns provided much better predictions than unmatched target patterns. These findings suggest that mental state and trait inferences are indeed connected. In particular, the brain represents others' traits as the weighted sum of their mental states by frequency. Given those promising findings, here comes the questions we want to address in the current work. Existing research that suggests there is a correlation between mental state and trait inferences all relied on quite artificial contexts, such as asking about famous people who participants do recognize, but probably do not know much about, or using static face as stimuli, while in real life, we see people move around in their natural surroundings. Therefore, first, we want to understand, does the correlation between mental state and trait inferences generalize to more naturalistic contexts? Study 1 and Study 2 address this question. Furthermore, it remains unknown whether there is a causal relationship between the two types of inferences. That is, does one type of inferences causally shape the other? Study 3 and Study 4 address this question. Okay, let's jump right into the first study. In this study, participants will show video clips and evaluate a given target in the clip. The videos are from a previous study by Chen and Whitney. All videos are colored and muted. They range from 30 seconds to 3 minutes. They include Hollywood movies, home videos, and documentaries. They also varied in the number of characters, ranging from 1 to multiple. We analyzed the mental state ratings and trait ratings given to the characters in these videos. The mental state ratings were obtained from Chen and Whitney's. Their participants viewed the videos and gave continuous ratings to the targets on valence and arousal. Valence describes how positive or negative the emotion is, and arousal describes how intense the emotion is. Valence and arousal are key dimensions that describe various mental states. Here is an example of the rating data for the video clips shown in the last slide across time and participants. Now we can condense this time series data into frequency data. We plot each pair of valence arousal rating for a given time point by a given participant into this two-dimensional valence arousal space. And we can do so for all time points and all participants in the time series, by which we end up with a frequency map that shows how frequently this target was given a certain valence arousal rating in this space. The brighter color indicates higher frequency. As I mentioned, valence and arousal are two key dimensions that describe various mental states. However, in everyday life, we don't just go around and say, oh, this person is feeling high valence, or that person is feeling low arousal. Instead, more often, we describe mental states using discrete labels available in our language, such as this person is feeling happy, that person is feeling sleepy. So we try to match the frequency of all the points in the two-dimensional valence arousal space to the frequency of meaningful discrete mental states. To do so, we projected a comprehensive set of 16 mental states that we have words for to the same valence arousal space. This projection was based on online participants' ratings about how each mental state could be described by the dimensions of valence and arousal. These ratings were from a period study by Tamia and colleagues. Then for each continuous point in the space, such as this red dot, we can match it to its nearest discrete named mental state, in this case, dominance. If we do so for all the points in the space, we will end up with such a nearest neighborhood partitions, where the color indicates how often a valence arousal rating given to the target in the video falls within that partition. Again, the brighter color indicates higher frequency. By doing so, we can represent each target as a vector of mental state frequency across the 16 mental states. For example, this is the police officer we saw from the video in the previous slide. And here is his frequency vector based on the ratings he received from the participants. And this is another target and a frequency vector. Using these vectors, we can compute how similar each pair of targets are. Next, we collected the trait ratings of the targets in the videos. Specifically, our participants were first told which one of the characters in the video is a target they are supposed to keep track of. This was indicated in a static frame from the beginning of the video where the target was first seen. Then before viewing the video, participants were asked to rate this target on different traits based on the first impression. Then they view the videos and rate the targets on those traits again after viewing the videos. At the end, we double-checked that participants remembered which was the target they were asked to keep track of. With these trait ratings, we can also compute the similarity between each pair of targets. Now to draw conclusions about whether mental state inferences and trait inferences are correlated, we can compare the similarity among the targets based on the mental state ratings and the similarity among the targets based on the trait ratings. We found that mental state frequency similarities and post-video trait similarities were correlated. This result indicates that people make associated mental state and trait inferences when judging targets in naturalistic stimuli. Interestingly, we expected that after viewing the video, participants should update their first trait impressions about the target according to the target's mental state they observed in the video. That is, mental state frequency similarities should be more correlated with post-video trait ratings than pre-video trait ratings. However, what we found was that mental state frequency similarities and pre-video trait similarities were also correlated, and to a similar extent as the post-video trait ratings. These findings suggest a directional relation between mental state and trait inferences. In particular, The trait impressions formed based on the static frame at the beginning of the video might influence mental state inferences throughout the video, but observing the target's actual mental states does not seem to lead to corresponding update in the trait inferences. However, we know that this finding provides only weak evidence of causation, which we investigate further in Study 3 and Study 4. To sum up, Study 1 shows that mental state frequency and trait inferences are linked in naturalistic context. However, it remains unknown whether this link generalizes to targets who are personally relevant, like our families and friends. Study 2 addresses this question. In this study, we asked each participant to name 10 people who they are personally familiar with. Then we ask participants to rate these familiar people on mental state frequencies and traits. For mental state frequencies, we have selected a list of mental states, like contemplating, shown here. We ask, how often is this person contemplating? That is, how often is this person thinking deeply and carefully? The participants rate the frequency on a 7-point scale for each familiar person. Based on these ratings, we can compute for each participant how similar their 10 familiar people are in terms of mental state frequencies. For traits, we have selected a list of traits, like extroverted shown here. We provided a statement. This is an extroverted person. That is, this person is outgoing, talkative, and sociable in general. And we asked participants to rate how well this statement describes each familiar person using a 7-point scale. Based on these ratings, we can compute for each participant how similar their 10 familiar people are in terms of traits. As what we did in the first study, we compared the familiar people similarity computed based on mental state frequencies to the familiar people similarity computed based on traits for each participant. We found that mental state frequency similarities and trait similarities were correlated. This finding indicates that people make associated mental state frequency and trait inferences when judging personally familiar targets in real life. To sum up, Study 1 and Study 2 show that inferences of mental state frequencies and traits are reliably associated in naturalistic and practically relevant contexts. Next, we turn to the causality question. Does making two targets appear to have different traits cause people to infer that they will experience more different mental states across a range of situations? Does making two targets appear to experience different mental states across a range of situations cause people to infer that they will have more different traits? Study 3 and Study 4 address these two questions respectively. In Study 3, we manipulate the target's traits and observe how participants make mental state inferences about the targets. To manipulate the target's traits, we use a short biography. We focus on manipulating the warmth and competence of the targets here, because they are two key psychological dimensions that describe how our perception of people are. In the biography, we have a short text that describes the target's warmth and competence. We also show a face that matches the text description. For example, this target is manipulated to have high warmth and high competence. So we selected a face that receives the highest warmth and competence ratings from a much larger face database. Here is an example of a different target who is manipulated to have low warmth and competence. Each participant views one target biography, and then the participants were asked to evaluate the target's mental state across different situations. For example, in this situation, imagine Mary is in an elevator. Which of the following mental state is Mary more likely to be in? In all situations, participants were provided with this same set of 6 mental states as options. These 6 mental state options were representatively sampled from a much larger set of mental states. For the selections of situations, we make sure that when there is no effect of the trait manipulation, none of the 6 mental states should be selected more often than the other across these situations. Based on the participants' choices across a range of situations, we can compute how often each mental state was selected for each target. And then we can compare whether the more different the targets were manipulated to be in terms of their traits will lead to more different inferences of mental state frequencies. Indeed, we found that the more dissimilar the traits that the targets were manipulated to have, the more dissimilar the inferences of mental state frequency they elicited. This finding indicates that manipulating inferences of traits causally shapes inferences of mental state frequencies. Next, we investigate the other causal direction. We manipulate the target's mental state frequencies and observed how participants infer the target's traits. To manipulate mental state frequencies, we use a statistical learning paradigm. Each participant was first told the name of the target they were going to learn about. There is no face used in this study. Then participants were shown a series of situations. For example, in this situation, imagine Olivia is with an annoying acquaintance. Then participants were asked which mental state is the target more likely to feel, tiredness or rage. Each situation is matched with a different set of 2 mental state options. These 2 mental state options were selected based on online participants' ratings, so that both mental state options were rated most likely to be elicited by the given situation. After participants indicate their answers, they will be provided with feedback whether their answer was right or wrong. For example, if I answer rage here, I will be told that Olivia actually experienced tiredness. This correct answer is designed to manipulate the target's mental state frequency, because across a series of different situations, we can calculate the frequency of the correct mental states that the target experienced. We design different correct answers for different targets so that their mental state frequencies are maximally different from each other. After learning the target's mental states across a range of situations, the participants were asked to evaluate the targets on a series of traits. For example, this is a question about the trait extroversion. Participants provided their ratings on a 7-point scale. Using these trait ratings for each target, we can compare how similar each pair of targets are. Finally, we can compare whether the more different the targets were manipulated to experience different mental states, the more different trait ratings they elicited. We found that, indeed, the more dissimilar the mental state frequencies that the targets were manipulated to experience, the more dissimilar the inferences of traits they elicited. These findings indicate that manipulating inferences of mental state frequencies causally shapes inferences of traits. To sum up this talk, I have presented you 4 studies that show that inferences of mental states and traits are not independent. Humans link these 2 forms of social information to gain deeper insights of other people. Inferences of a target's traits causally shape how people infer the target's mental states across a range of situations. And inferences of a target's mental states across a range of situations causally shape how people infer the target's enduring traits. We hope that integrating this bidirectional causal relationship between mental state and trait inferences in AI design would enable a more flexible machine theory of mind. To end this talk, I would like to give a big shout out to my postdoc advisor, Mark Thornton. I've learned a lot of new skills and new ways of thinking during this collaboration. I would like to thank Diana Tarmia for sharing study materials, my labmates Landry Booth and Lindsay Tupfer for their helpful input. I would like to thank my PhD advisor, Ralph Adolphs, and labmates Umi Callis and Dori Clayman for their constant support. Finally, thank you all for participating in this talk.